and this begins EE 544 on Thursday, February 13th, 2014.
Thank you very much. Good afternoon, everybody. Let's continue our discussion from last time. Let me use the pad, and we'll get to the charts later on. The noise modeling. And let's see if you remember, we were talking about what? Noise generated by a resistor. This is a quick review from last time. This is R, and this is a what? A noisy resistor. This one can be equivalent of this is a series. This is R. This one is what? Noiseless resistor. Okay, and this one is what? It's the square root of what? 4KTBR. This is what we refer to as what? Vn square root, which means what? It's the root mean square. The root means square voltage, noise voltage. If you remove this square, what is it becomes? It becomes a measure of what? The power. The mean square is a measure of what? A power. Clear? The average power of the noise. Clear so far? Okay. Now, this one, again, as I told you, we need, this one is called what? Thevenin's equivalent. Clear? You could also write it in what? In the Norton's equation, but instead of a voltage source, it becomes a what? A current source. Now, let's take just a simple example just to make sure that you got the idea. Let's assume that we do have this circuit. Vs. Okay, and let's remove this one. This one is what? R1. R2. R3. And this is the what? The load. Clear? And this is R. Tell me, how do I find the equivalent of this? Yeah, by the way, what is this Vs? That's the source voltage. What source? When I say source voltage, this for the signal, not for the noise. Do you follow me or not? This is for the signal. Now, what do I do if I want to find the equivalent? This, the Thevenin's equivalent. So what do I have? I have this. What is this? Tell me, what is this? How do I find this? Still waiting. By the way, is this noiseless or noisy? Noiseless, because I incorporated the noise in here. Yes? But what is its value? Seven. Still waiting. 7 inches. What do you do? How do you find the resistance here? Using Thevenin's. Did you forget about this? This is EE, I don't know. It's what? What do you do to the source? Short circuit. So what do you have? R1 in parallel with R3 in series with what? R2. So what is this? R1 in parallel with R3 in series with what? R2. Yes or no? Okay, so what is this? What is Vn? Give it to me. It's 4 K T B R T. Where RT is this guy. Yes or no? Okay. And what is the K? By the way, what is the temperature? What is the T? I'm sorry. What is the T? Temperature. And what is the K? It's Boltzmann. Constant. Anybody? Value? Anybody? 1.38 times 10 to the units joules per what? Degree Kelvin. Now, most of the time in our equations, it's later on. Most of the time, we will change it to what? To the dB stuff. Are you following it? To the dB stuff. It will be minus 228.6 dB. But let's not worry about that right now. Clear? Okay. What is this, by the way? What is this guy? Yes. What is this voltage? Is it Vs? This is a voltage looking at what? Here, with this one being what? Open. Yes or no? So what is it? R3 divided by what? R1 plus R3. Did you get it? This one does not get into the picture. Yes or no? So this one is what? Vs times what? R1 plus R2. Sorry, plus, I messed up? Sorry, R3. I'm sorry. R3 divided by what? R1 plus R3. Did you get it? Yeah? But I don't care about this. This is not what I care about. This is what I'm caring about. Clear? Okay. Now, we also saw what? The power, the noise power delivered to the load is the maximum power. And when does this happen? And is the maximum power, and it happens when the load what? When the load is what? Matched to the what? To the source. So if we go back to the, if we go, this is all from last time, quick review. If we go to this is R. This is this is noiseless. This is noiseless. And then what? This is the what? Load. Yes? Matched. Notice, by the way, when we get to the matching, we will see actually when we say the load is matched to the source, what we mean by that is the what? Is the conjugate. Did you understand that or not? It's the conjugate. In other words, if this one does not need to be a pure resistor. But if it is a pure resistor, they will be what? They will be equal. But if it is not, then it needs to be what? The conjugate of it. Okay, what did we find? We found that the power, the noise power delivered, bless you, noise power delivered was equal to what? K. Did I show you this last time? Yes. Which is what? Independent on what? On R. KTB. And of course the unit is what? Watts. Clear? Clear? Okay. Now, how about if we do have a passive element? In other words, it's a passive circuit, but it's not totally what? Resistive. In other words, let's look at this. Consider now the following. Passive circuit. Let's say this. What is the noise power delivered at the output? By the way, this one is what? Is noisy, and I'm going to what? I'm going to replace it by a what? A noiseless resistor, and what here? That is the Vn square. Are you following me or not? The mean square. If you are voltage, then this one is what? Is square root. The root means square value. Yes or no? First of all, answer me the question. Does C introduce noise? No. By the way, I'm assuming that there is no what? There is no parasitic resistor. That's a pure what? That's a pure capacitor. Yes? Okay. So what does that mean? What does that mean? What is its effect? You have to understand one thing, is that even though it does not introduce what? Noise, but it will shape the spectrum of the noise. The noise in this case is no longer what? Is no longer constant, not a function of what? Frequency. Did you understand what I just said or not? So even though here, see the capacitor or inductor, for matter if there is an inductor, capacitor will not introduce what? Noise, but will what? Shape. Why is it shaping? This is acting as a filter, as a low-pass filter. Yes or no? Okay, but will shape the spectral, the power, spectral density of the what? Noise. Yes? So how do we calculate the total noise power at the output? Total still waiting. What is going to change from this? This is the power, it's the 4K, it's VN is what? Answer me the following question. Is this constant? That's constant. Yes or no? Is it a function of frequency? It's not a function of frequency. That's where. Where is this? This is this guy. I would like to know what is the power in here, the noise power. Yes? It's what do I need? I need to figure out how is this one is shaping, how is this one is shaping? Yes or no? Which means what? It means that I need to integrate, in other words, see this one here? What did I do? I multiplied by what? B. Yes? In here, what do I need to do? I need to integrate over what? Over all possible frequencies, because the response of the system is not going to be what? Flat. It's not going to be constant. Yes or no? And instead of R, what do I need to take? I need to take the what? The real part of the input impedance. Are you following or not? What is the input impedance? What is the input impedance? Looking at this these two terminals. What is the Z? Z equal to what? Help me. SR plus what? 1 over what? J omega C, which is what? Which is, help me, which is 1 plus what? J omega RC, did I mess up? Over what? J omega R, J omega C. You agree? Okay, now listen to me. Is it a function of the frequency? It is a function of the frequency. Now, what is the voltage here? Is this a voltage division circuit? That's a voltage division circuit. What is the voltage in here? The voltage in here is what? Is this impedance, which is what? 1 plus, what is what? 1 over J omega C divided by what? This whole thing. You agree? Which means what? The 1 over J omega C will cancel this one out. Yes? So what do I end up with? Are you following me or not? And of course, the what? Absolute value of H of omega is what? You agree? And then what is the total output noise power? Total noise power at what? What is it? It's equal to what? 4K T B, R, yes? Now, but I cannot write B. Why? Why I cannot write B? Because this is not a flat. So I need to what? I need to integrate of what? 1 plus omega square, R square, C square, D what? D omega. Now I think there is also a what? A 1 over what? 2 pi factor. Are you following me or not? Cannot hear you. Why is that? Why is that 1 over 2 pi? It's because it should be what? To dF. Are you following me? This is d omega. So when we talk about power spectral density is what? In watts per hertz. This one is what? It's watts per what? Radians per second. So you need to multiply by 1/2. Now, I will let you do this at home, this simple integration. By the way, this is from where? Minus infinity to infinity. Are you following me or not? Cannot hear you. Okay, if you do that, this is what you get. I will let you do this at home. Something strange. Can you tell me what is the something strange? This is the noise power at the output. Yes? What is the strange thing about this? By the way, you might say, Professor, where is this R going to go? You have to remember this one will be what? A tan inverse stuff. Are you following or not? And the derivative, you need to take it in here, it will cancel. Did you get this or not? Okay. Where is the, does it depend on R? Does not depend on R. And I am waiting for why. I am waiting why. Now listen to me. Listen to me. When you increase R, what will happen? The noise power will what? Increase. What will decrease? Excellent. The bandwidth will decrease. Why? Because when you increase R, the time constant, which is what? RC. The bandwidth is what? Inversely proportional to RC. Are you following me or not? And since the what? Since the noise depends on R and the bandwidth, one of them will what? Decrease. The other one will what? They will cancel each other. Do you understand that or not? Yes or no? You will see it by solving this thing here. Clear? Okay, good. Now, let's continue. And we start, this is, I think, where we left, we ran out of time. Next, we are going to be looking at what is known as what? The noise figure. Let's set it up so that you understand what we are talking about. This is what we have. We have an amplifier. This is with a gain of what? G. That's an amplifier. With a gain of what? G. There is a what? There is a source in here. There is a source in here, a noise source, that is what? Generating the power of what? K, T, B. What happened to the R? What happened to the R? We are assuming what? We are assuming that the input what? That the input resistance to this gain is the same as what? The resistance of the source that is generating the noise. Did you get my point or not? Yes. So this is the input noise. I'm going to designate it by what? N sub I. N sub I, the input noise power is what? KTB. Clear? Of course, in series with what? With the signal. And let's assume the signal power is what? SI at the input. This is the signal power. Clear so far. So we have an amplifier. You applied the desired signal. This is the signal, useful signal. And there is a what? There is a noise. Could this one coming from an antenna? Could this noise coming from the antenna? It can come from the antenna. Are you following me? Not from any resistive or source of noise. This one, I'm lumping it as what? KTB. Clear? Okay. I am measuring the output, signal power, and the what? Noise power. Okay. By the way, there might be some confusion, which I hope that will not. Remember, for white noise, what did we say? For white noise, we said that the power spectral density for white noise looks like what? And what did we say the value? This N0 has nothing to do with N0. Do you understand that or not? This N0 is, we are designating the what? The output noise power. Are you following or not? Whereas this one is the what? Is the white noise power spectral density. Clear? By the way, will this one be white? Will this one be white? Of course not. This amplifier has a what? Has a frequency response. It's not going to pass what? All the frequencies in there. Did you get this or not? Yes or no? Yes. Okay, so this is the output signal power. And this is the output what? noise power. So at the beginning, what did they do? They look at what? The input. They measure the signal power. They measure the noise power. Signal to noise ratio at the input is what? SI over NI. Yes? They believe that what? The output signal to noise ratio should be the same. Why? Because the amplifier is amplifying both the signal and the what? Noise. They discovered it's what? It's not the same. It's less. That tells them what? Tells them that the device itself is introducing what? Internal noise. So they try to what? To model that. How do they model? Let's see. So they defined a parameter, which is called what? The noise factor. The noise factor. It's not the noise figure. Noise factor. Which is defined as what? The signal to noise ratio at the input divided by the signal to noise ratio at the what? Output. And since they found out that the signal to noise ratio at the output is smaller than the signal to noise ratio at the input, the noise factor is a measure of the degradation. If the signal is being what? I mean, the quality of the signal is being what? Degraded. Did you get this or not? So this parameter, this noise factor is measure of what? Degradation in the what? In the amplifier. Clear? Okay. Now, what is the next dilemma that they faced? The next dilemma that they faced is what? Is that this is a function of what? It's a function of what? Temperature. And they did not want to define what? A noise factor for each temperature. In other words, in this specification, you are not going to see what? A noise figure when the temperature is this. A noise figure is when the temperature is this. They want to define or put a universal definition for what? For the noise factor. Clear? So this definition is applicable only when what? When T equal to what? T0, which is the what? Room temperature. And there is no question in my mind, I hope I'm wrong, there is no question in my mind that some of you will make a mistake in the midterm using this equation when the question does not tell you that the system is at what? Room temperature. Why I'm saying that? From prior what? Experiences. I hope I'm wrong. Did you answer what I just said? This equation is used only at what? Room temperature. Clear? Okay, so what do I have? What is it? S and R. What is it? SI divided by what? NI. What is the output signal power? The output signal power is what? G SI, yes or no, divided by G NI plus what? NA. A means what? Added what? Internally. This is the noise power that is added internally as observed on which port? On the output port. This is crucial. You need to understand it. This is because when I put it here, I'm looking at where? At the output. So this one added internally on the what? Based on what? On output port. Or reference, sorry. Reference. On to output port. Clear? Okay. Now usually, they are usually referenced to the what? To the input port. We will see that in just a second. Are you following me so far or not? Okay, so what do I have? Okay, the SI cancels with this SI. Clear? So what do I have? What do I have? This NI will be with this. In other words, what is it? F is equal to what? Help me. G NI plus what? NA. One more time. This one reference to who? To the output. Divided by what? G NI. Which is equal to what? 1 plus NA divided by what? No. G N I, not G sub Ni, G N I. Yes? G N I. Clear? Clear? Okay. Now, by the way, what does that tell you? It tells you that the noise factor is greater than what? It's greater than what? You are not going to be what? You are not going to get improvement on the what? On the signal to noise ratio. Clear? The best thing you could do is what? Is that there is no degradation, no noise introduced by the device. Okay. Can I bring this one to this side? So what do I have? N A is equal to what? G N I times what? F minus 1. Are you following me so far? Which is equal to what? G K T B times what? F minus 1. Did you get it? What is this T? I'm sorry. What is this T? T0. Because we are dealing with what? T0. That's the definition of the noise figure. Yes or no? Cannot hear you. This G is this G. The Ni is what? Is KT0B. And then what? F minus 1. Yes? Now, I want you to see how we are going to model this. The G is the what? Is the gain of the amplifier. Yes? Which means what? It means as if I had a what? Another source here. In other words, the resistances that what? Sorry, the noise that has added internally, it's equivalent to a noise being generated at the input with what noise power? Remember, when I say at the input means what? Don't include the G. Which means what? We already know that what? That the noise power is what? KT times what? B. The K is already here. The B is already here. So what does that imply? It implies as if we have a source at what temperature? T0 times what? F minus 1 at where? At the input. Did you understand that or not? This I'm going to define. T equivalent equal to T0 times what? F minus 1. Clear? Answer me the following question. Is this a real temperature? No. That's not a real temperature. Do you understand what real temperature means? That's not a real resistance. Clear? This is the what? The equivalent noise temperature of the what? By the way, what does that imply? It implies that F is equal to what? 1 plus what? T equivalent over what? T0. This equation, whatever the equation is. Let's put this one equation 1. This equation 2. Clear? Yeah, how am I modeling it? Look now. This is now. What do I write about this amplifier? Noiseless amplifier. Yes or no? G, the gain is G, noiseless. And what do I have here? I have two sources. Yes? One of them is at what temperature? One of them is at what temperature? T equivalent? Yes or no? And the other one is at what temperature? At what? T0. Did you get this or not? Yes or no? This one generating what noise? Ni equal to what? K T0 B, whereas this one is generating what noise? K T equivalent times what? B. What is the noise output power? What is N0 equal to? G times what? K, T equivalent, B plus what? K, T0, B. Did you get it? Yes or no? Yes.
Yeah, this equation is still only valid when the T0 is 290 degrees.
That's the room temperature. That's the room temperature, which is what? 290 degrees.
So if T0 is different, we cannot use the equation.
You cannot use this equation. You cannot use this equation. And I will show you what to do in just a second. Do you understand that or not? You cannot use this equation. Clear? Yeah. This equation is only for what? For room temperature. That's what I meant by saying a moment ago. Some students get the idea that what? That they can use this equation no matter what. Okay. By the way, most of the time, the source will not even be at a room temperature. If the source is an antenna and the antenna is mounted outside, if it is cold outside, the temperature is low. If it is hot outside, the temperature is what? Hot. So, it's not room temperature necessarily. Clear? Clear so far? Okay. So now, what did we say? We say the equation, again, it's F. This F is equal to what? 1 plus what? T equivalent over what? Over T0. Clear? The best thing to do, by the way, is to work in temperature and then change it to what? Change it to what? Change it to, or relate it to the what? To the noise factor. Clear? As I will show in just a second. Did you understand this or not? Yes or no? Okay, good. Now, how do we measure? How do we calculate? The noise figure, the noise factor. Let me write one thing here, please. The noise figure is equal to what? 10 log the noise what? Factor. All the equation that we are going to see is the what? Is the noise factor. At the end, you need to take the what? 10 log. Clear? Okay. How do we calculate the noise factor of a lossy line or a what? A filter. What comes at the receiver front end after the antenna? After the antenna, before the LNA, we have some kind of what? We have some kind of what? Of a wire, a refined cable. Are you following? That's a lossy line. And if you have a what? If you do have the band select filter, that's a filter. Did you get this or not? Okay. A lossy line or a filter, yes? Okay. Which is matched at both sides. At both sides. There is no question mark. Yeah, there is. There's a question. I thought, clear? So what do I have here? I have a noise source generating what? So this is Ni equal to what? K T B. Are you following me on that? Question. Is this room temperature or this is just the temperature? That's the temperature. That's not a room temperature. So this is a what? The temperature. And then what do I have? I have a resistor, and this one is what? Noiseless. Because I already, the noise, I already covered it here. Are you following me on now? And then I have a what? What is this? That's the transmission line. By the way, we will, even though it's really not part of this course, but I need to make sure that you do understand that. So next week we will have one lecture or two lectures on the transmission lines. Clear? Okay. What is the transmission line? The transmission line is what? Is G, the gain, which is really what? Let's write it like this. G equal to what? 1 over what? L, where L is the what? The loss. Are you following me on that? Now, and then what? Z naught. Are you following me on that? Z naught, which is the what? which is the characteristic impedance, and then what? A matched load. This is a matched load. R, all of them are R. Are you following me or not? Usually it's what? Z not anybody? 50. Clear? Usually 50. Clear so far? Yes? No response. Yes? I would like to find what? I would like, is this one going to add noise? This one is going to add noise. Are you following me or not? I would like to know what is the noise factor of this guy. What is the noise, in other words, what is F of this guy? Now listen to me. We have a matched two ends from the source side and from the what? Destination side. Which means what? There is no reflection. The system is at equilibrium. Do you understand that or not? There is no reflection there because it's matched on both points. Clear? What is the power generated? What is the power generated by this source? By this source. It's K, T times what? B. Are you following me or not? Yes or no? What is the power delivered to the resistor? What is the power delivered to the resistor? The system is at equilibrium. Equilibrium means what? It's matched from both sides. Yes or no? What is the power delivered to the resistance, to the load? It's exactly the same as what? As the input. Do you understand that or not? Yes or no? So the question then becomes, but then why did I say that this is a lossy line? I'm not sure, did you get my point? Did you get my point or you lost me? You lost me. Can we concentrate a little bit? The telephone line, the transmission line. Is at thermal equilibrium. Matched on both sides. Clear? The output power, noise power is K, T, B, which is equal to what? The input noise power. Yes? What input noise power? When I say input noise power, what input noise power? This guy, this source, antenna. Let's assume it's the antenna. Yes or no? Cannot hear you. But the line is lossy. That's why we put an L. What does it mean? If I tell you that the output noise power here is the same as the noise power generated by this source, what does it mean? It means the system is introducing what? Internal noise power that when it added to this one, with the loss, you will get the same as what? The original. You lost me. Did you lose me? Hey, you lost me. I can tell you lost me. Can we concentrate? Okay. What is the input noise total? What is the total? Let me write this one. Input noise power from where? From external source. What external source? Where is the external source? Antenna or whatever the case might be. This could be what? The output of a signal generator. Are you following me or not? What is the opposite of external? Internal. Internal is the one that is generated by what? By the transmission line or by the filter. Yes? Give me. What is the total input noise power? Still waiting. What is it? It's K, T, B. Yes or no? Is this room temperature? No, it's KTB. Plus what? K, T, equivalent B. What is that? Can you tell me what is this? What is this term? This is the noise power added by who? By the transmission line, reference to who? To the input, not to the output, to the input. Yes or no? Yes. And then what? Everything is multiplied by G. No, I need to write this one separately so that you understand. Did you understand the total input power? Yes. So now what do I have? G times what? In a minute I will replace the G by 1 over L. For time being, just write the G. K. T. What is T equivalent? What is T equivalent? It is what? T0 F minus 1. Is this T0 or is it T? This is T0. In other words, don't confuse this with this. This one is the temperature of what? Of the external source. Whereas this T0 is because we use the definition of what? Of the noise figure, or sorry, of the noise factor. Yes or no? The signal to noise ratio at the input is equal to, divide by signal to noise ratio at the output. Yes or no? Well, give it to me. What is it? What is T equal? T0 times what? F minus 1, close the bracket. Yes? B? What B? Here. B. I'm sorry. B. Yes? What should this one be equal to? KTB. Why? Why? One more time. Why should this one be equal to KTB? The line is at equilibrium. There is matching between what? Between the input, the output, and the what? The characteristic impedance of the line. We say that the line is at what? At equilibrium. There is no what? There is no degradations in the what? In the power. Yes or no? But this is what? Added internally. Are you following? This one was not an external. Is this external source? This is not an external source. This is an internal source. Did you get my point or not? Yes or no? So now what do I have? Can I cancel the B? Can I cancel the K? So what do I have? K, B, K, B, K, B. So what do I have? Help me, help me. Can I bring the T here? So what do I have? T, help me. 1 minus G is equal to what? T0, I messed up. G times what? Did I mess up? So what do I have? F is equal to 1 plus T over T0. No, I messed up. 1 second. One more time. One more time. F is what? T 1 minus G over what? T0 G plus 1. Clear? Okay, and that's equal to. What is 1 over G? What is G over G? 1. So what do I have? L minus 1 times what? T over T0 plus what? 1. That's the noise factor of the lossy transmission line. Clear? Clear? Now, if, let me write one statement and I will get back to you. If T happens to be equal to T0, what is F equal to? Do you understand that or not? Yes or no? No response. Yes or no? Okay. This is only if T is equal to what? T0. If T is not equal to T0, then the F, you need to calculate it from this equation. And in the midterm, I will definitely give you the case when T does not equal to T0. So that I make sure you don't make the mistake. Did you get it or not? Yes or no? Did you understand this idea? So the line is lossy. The aggregate input noise will be what? Will be degraded because of the loss, but the received power is the same as what? The power that was generated by the external source, because you have what? You have matched condition. The transmission line, we call it in what? In equilibrium. Did you get my point or not? Yes or no? Yes.
Did you just go to the other page?
What other page? This page?
No, the last one.
This is the last one. Oh, this one? Here.
The one after?
What there is? Oh, sorry. I don't. Yeah, one second. You don't need to say please.
Is it allowed to use T equivalent here if the T is not equal to T?
My dear, this T equivalent has nothing to do with T. And this is the point that I'm trying to make. This T equivalent, does it have anything to do with T? It has nothing to do with T. This T equivalent, one more time. Is this T equivalent a real temperature? It's not a real temperature. It's not a real temperature. It has nothing to do with T. T is the temperature of the source. The noise generator or the antenna, whatever the case might be.
But we derived it on the...
This one, we derived it based on the definition of what? T0. And that is why in here I wrote it what? In terms of T0. I wrote the T equivalent in terms of T0 because I'm using F. In here, in the definition, is there an F? The F is defined only, this equation is when what? When the device is at what? Room temperature. Do you understand that or not? Okay, by the way, here, let me ask a question. If this is not at room temperature, sorry, this is the source. Where is it? Here. Does the transmission, could the transmission line be indoors? The transmission, no, it cannot. In other words, could the antenna be outdoors, but then the cable to the indoor? Which means what? Temperature has nothing to do with each other. Did you understand that or not? This T equivalent is just a what? A make-believe temperature. It's not a real temperature. Did you get my point or not? It's not, it's not, make-believe means what? It's not a real source. It's generated internally.
So the noise doesn't have to be at room temperature to use the T equivalent equation. We can use the T equivalent equation.
This T equivalent is for what? For the device. Any device. Can you hold a second? You have no choice. Hold a second and I will show it. Did you get this or not? Yes or no? Okay, good. Now, let's look at a bigger picture. How do we calculate the noise figure? The noise factor of a chain of devices. Now, I'm going to show you, of course, only two. Once you get the idea, you get the idea. You follow me or not? I'm not going to show you. By the way, do we have only two devices in the... We have multiple devices, but once you get the idea, that's enough. So now what do I have? Let's see if you can help me. What is this? G1, yes, F1, T equivalent 1. This is for device 1. And then what? Another device. By the way, when I sketch it here, it gives the impression that it has to be an amplifier. It could be any device, a mixer or a filter or whatever. Yes? Okay. And this G1 could be what? Could be higher than 1 or it could be what? Lower than 1. Clear? Okay. And I have another device. G2. F2. T equivalent 2 is the output and this is the input. Clear? Clear? Now, what is the input power here? The input power, the external input power is what? KTB. Are you following me on that? Now, what do I want? I want to find G equivalent, sorry, not G, G total, I don't want to put any subscript, G F T equivalent. Did you get this or not? What is this? What, by the way, what is the input noise power here? Is the input noise power here the same as this one? Is the output noise power the same as this one? Yes, it is. I want to what? What is the, I want to what? I want to find the equivalent of these two. In other words, if I can replace these two devices by one device, what will be the what? The noise factor, what will be the equivalent temperature, what will be the gain, and so on and so forth. Now, of course, the gain is straightforward. What is the gain? It's G1, G2. Or if you are in dB, it's what? G1 plus G2. Clear? Okay, but let's take it step by step. Yes? What is the power here? What is the noise power here? Total noise power. The total noise power here is what? K, T, B, yes or no, plus, still waiting, K, T, equivalent, 1, B. Are you following me so far or not? Yes or no? Now remember, what is this T equivalent 1 equal to? This T equivalent is equal to T sub 0. T sub 0 times what? F minus 1. Are you following me or not? Okay, keep that in mind. Now, what is the power here? What is the noise power here? The noise power here, I messed up the diagrams, but that's okay. What is it? G1 times what? K, T, B, plus what? G1, K, T, equivalent, 1, B. Am I done or not yet? What is it? K, T, equivalent, 2, B. What is this? Can you tell me what is this? That's the internal noise generated by this device as referred to where? As referred to the input. Yes or no? Okay. By the way, how come I'm adding the power? I'm adding the power because I'm assuming that the sources are what? Independent, uncorrelated. And since they are Gaussian, then they are what? Independent. Did you get my point or not? Yes or no? Okay. Now, what is the output power? Here. N0. I'm still waiting. G1, G2, K, TB, plus G1, G2, K, T equivalent, 1, B, plus G2, K, T equivalent, B. Did you get it? Yeah, this is only G2, not G2, G1. G2, just G2. Yes? Okay. What is the noise power? What is the noise power at output of the equivalent system? Let's put this one equation. By the way, I lost track. One, what the equation A? Okay, what is it? I'm still waiting. Is it, by the way, is the source the same? Yes. The noise source is the same. So it's what? G, K, T, B, plus what? G, K, T equivalent, B. No subscript. No subscript. Yes or no? This is equation what? B. Clear so far? Yes or no? Okay. Now, the equating equations. B, A, and what? B. Tell me, what do I have? I'm still waiting. This term, do you see this term and this term? What does it tell you? G equal to what? G21, G2. Did you get this or not? Now, what does this term tell you? G, K, T equivalent, B. Yes? What is it? Give it to me. What is T equivalent equal to? Okay, let's do it in 2 steps. You lost me here. You lost, did you lose me? So what is it? Say that again. Which G? Did you get it? Do I need to show you this step by step, or did you get it? Did you get it or not? Step by step. Okay. Now, what do you see missing? What do you see missing in T equivalent? Because that comes to your question a moment ago. What do you see missing? You don't see a T. Are you following or not? You don't see a T. You just see a what? A mythical equivalent temperature. Are you following me or not? Yes or no? Okay, good. Now, so this one equation, C. Too many A, B, C. Too many equations. Now, what is F? Equivalent, total, equivalent. What is the total? By definition, first of all. By definition, it's what? What am I going to use? This definition. Did you understand that or not? That's a definition. Measured at what room temperature? Oh, sorry. Measured at what temperature? The room temperature. Definition. So it's what? 1 plus what? T. Equivalent over what? T0. Yes or no? Yes. Okay. Now, listen to me. Divide this by T0. Can I divide this by T0? Yes. I divide this, every one of them by T0, by T0. Yes or no? Okay. What do I get? Equal to. Still waiting. 1 plus. Agree? You lost me? Did you lose me? The F equivalent 1 plus T equivalent over T0. Which means what? I'm going to divide this one by what? T0 and I substitute. Clear? Clear? What is this equal to? What is T equivalent 1 divided by T0? Here. T equivalent 1 divided by T0 is what? F1 minus 1. Yes? The 1 will cancel with this one. Yes or no? So what do I get? F1 plus, what is this? F2 minus 1 over what? G1. Clear? Clear? That is why I tell you I prefer that you work in what? In the temperature, and then what? And then change it to what? Change it to the noise factor. Do you follow me or not? It's easier to see it that way, that the T will what? Will cancel out. Did you get my point or not? Okay. Can you tell me what is the general thing? Before we conclude. Can we, when I say before we conclude, does not mean we conclude the class. The class still going on before we conclude this. Help me. So, to generalize. Still waiting. F1 plus F2 minus 1 over what? Next one. F3 minus 1 Do I need to continue or did you get the idea? Okay. Can you, by the way, can you tell me what is the T equivalent? The T for the extended case, for more cascaded systems, is what? T equivalent. T equivalent 1 plus what? T equivalent 2 divided by what? G1 plus T equivalent 3 divided by what? G1 and G2. There is no minus 1. In the temperature, there is no minus 1. It's just by itself. Clear? Clear? What do we conclude? Help me. What do we conclude? We conclude that the overall noise figure, noise factor, no, these, by the way, I forgot to mention, this is not in what? dB, which means these are what? Noise factors, not noise figures. The question will give it to you in what? In dB. Do you understand that or not? Do not plug. You need to change it into what? Non-dB before you plug. Clear? Okay. Help me. We conclude that the overall noise factor of the system is mostly covered, mostly influenced by the first device in the receiver chain. Clear? Clear? Why? Because these are going to be what? These are going to be divided by what? By some gains. Are you following me or not? Can I increase those gains so that their effect becomes totally what? Negligible? Can I increase the gains, these G1 and G2 and stuff? The received signal is weak anyway. Can I increase it right away? We saw last time that if you increase the gain, if you put all the gain in one unit in the front end of your receiver, the front end of your receiver will go into what? Into saturation. And if there is a what? If there is a blocking signals in the vicinity of the desired receiver, it will cause what? It will cause interference on the same frequency as the desired signal. You will desensitize your receiver. Did you get this or not? Okay. Now, what is the first device? But you need to be careful. The LNA, unless if you attach the LNA to the antenna, which some, by the way, some systems do. Are you following me or not? Then it will be the first device. But if it is not, when the antenna, you are going to what? Extend cable. Let's assume your receiver is indoors. Your receiver is indoors, but the antenna is what? Outdoor. Yes? So you are going to extend the cable from the antenna to what? To the receiver inside. That transmission line, we just saw that it will introduce what? It will introduce some losses. And when it introduces some losses, what does it mean? It will introduce also degradation in the noise factor. Clear? So you need to look at this carefully. And again, finally, the noise factor, the noise figure is 10 log the noise factor. Clear? No response. Clear? Okay. Now let me show you one numerical example from the chart so that you can see the calculation. Okay. By the way, in the chart, the equivalent is what? Is the N. So don't get confused. When you read the chart, this one is what we refer to as what? Equivalent. Are you following me or not? The author here, I think this Lee, uses what? Uses N. So don't get confused. This equation that we just derived. Okay. Now, let's look at just a general equation. Simple equation. Sorry, simple. I said equation. I'm sorry. A simple example. What is it? We have a cascade of a what? Of the LNA and a mixer and a VGA. What is a VGA? The variable gain amplifier. Now, the question gives you the what? The LNA has a gain of what? 20 dB. Noise figure is what? 2 dB. Relatively what? Relatively small. You follow me or not? Relatively small. The mixer has a conversion gain of 10 dB. What does that tell you right away? It tells you that this is an active mixer, not a passive mixer. Passive mixer will not give you a conversion gain. What do I mean by the way conversion gain? I might have forgotten to ask you before. Did I explain to you what a conversion gain of a mixer mean? Yes, I did, but you forget. The conversion gain of a mixer, this at the receiver, is the power at what? The average power at the IF divided by the average power at the what? RF. That is what is referred to as what? The conversion gain. We'll study it when we get to the design of mixers. So, conversion gain of 10 dB, noise figure, 12 dB. That's a what? Very noisy mixer. Are you following, Anna? Very noisy mixer. Think about it as what? You are mixing some fruits to make what? A drink. Noisy or not noisy? It's a joke, it's a joke. You have no sense of humor. You have no sense of humor. The VGA has a maximum gain of what? 60 dB. You notice, by the way, the VGA is what? It's not on this side. It's on this side. By the way, I'm omitting a lot of filters in there. Keep in mind, after a mixer comes a what? A filter. But it's not shown. It's just a numerical example. Okay, 60 dB and the noise figure is what? 20 dB. Okay, so now what do we have here? As long, by the way, you notice this, as long as each stage is what? Impedance matched. Because if there is no impedance matching, you are going to have what? You are going to have some reflections. Are you following me or not? We'll talk about that when beginning next week when we get to the impedance matching stuff. Okay, as long as we can apply the cascade formula. What is it? 10. Which equation am I using? What is this? 10 log 1.58. This is the 1.58. Yes, where is the 1.58 came from? 2 dB. That's the 1.58. Plus 15.85. Where did this came from? That's the 12 dB. 15.85 minus 1 over what? 100. Where is this 100 came from? That's the 10 dB. Sorry, that's the 20 dB. Plus what? 100. Where in the world 100? That's the 20 dB. 100 minus 1 divided by what? 100? 10. Where did 10 came from? That's a conversion gain. By the way, did this get into the picture? This one did not get into the picture. Clear? You ended up with what? 2.63 dB. How much was the noise figure for the amplifier? For the LNA? 2 dB. So it's just a little bit more than the what? More than the LNA. Clear? Clear? Okay, good. Now, let me go back to the charts and I show you one more parameter, very important. We need to understand it carefully, which is what? MDS. What is MDS stands for? Minimum detectable signal. Page 12. By the way, a couple of charts, we will leave it when we get to the, by the way, the noise we will revisit again. Definitely we will revisit again when we get to the, the actual circuits. So I'm going to leave this part, but I just want to make sure you do understand what do I mean by a reciprocal network. Is this the first time you hear about this or you have seen it before? What is it? What is, when you say a network is reciprocal, what does it mean? What, it means what? It means that when you apply a current at the input port and you measure the what? The voltage at the output port will be the same if you apply what? The same current at the output port and you measure the what? The voltage at the what? At the input port. That network is called a what? A reciprocal network. And this shows you how to calculate the noise figure for the reciprocal network. But I will leave this when we get to the discussion of the two-port networks. Clear? Two-port networks means what? Means, for example, the amplifier and so on. So clear? So we'll leave this one for a minute. Okay, define it for me. Minimum detectable signal. This is the smallest. Smallest means what actually? The weakest received signal required to maintain a minimum, a given minimum signal to noise ratio at the output of the receiver front end, i.e. the input to who? Remember, the RF receiver is what? The RF receiver front end is just what? Amplification, down conversion. Yes or no? Channel, select. Yes? What should comes next? No. Before the ADC. You need demodulation. You follow or not? You need to demodulation. You need to get rid of the carrier. But by the way, if that is the case, if you are using direct conversion, but we are talking about in general, this is the super heterodyne. Are you following me or not? Okay, so it's the input to the what? Clear? Clear? So this is what we have. What is this? This is the equivalent front end. Are you following me? In other words, this is the F total. This is the F total. This is the what? T equivalent total. Did you get this or not? This is the what? G what? Total. Are you following me or not? And then what do I have here? The demodulator. And what do I want to maintain? I want to maintain S0 over N0 minimum. Why? Why? What does it depend on this guy? What is the thing that will depend that I don't want to make the signal to noise ratio here is too small. I want to have what? A minimum value. I don't want less than that minimum. Where are you going to measure your BER? What is your BER stands for? Bit array. Where are you measuring it? You are measuring it at the output of the demodulator. Yes or no? Which is a function, this BER is a function of who? The signal to noise ratio. Where? At the input of the demodulator, not at the input of this. By the way, what is the signal to noise ratio? Well, can you tell me what is the noise power here? The noise power here, if it is thermal noise, what is the power of a thermal noise? Thermal noise, the white noise. The white noise. What did we say? Yes? N0 over 2. What is the power? Noise power. Infinity. The noise power is the area under the curve is equal to infinity, which means what? It means no matter how strong your signal, the noise will what? Eat it alive. Did you get this or not? But luckily for us, we are not listening to the signal here. We cannot hear it anyway. Did you get my point or not? We cannot hear it. So it will go through what? Multiple of filters that will get rid of as much noise as possible. What we want is that we want to maintain the signal here. And we want what? What is the what? What is the signal? What is the minimum signal? Yes or no? Yes or no? Let's see if you can help me. Now, what am I going to assume? I'm going to assume that this is the source of the noise. Yes? Yes or no? This is, we are going to refer to it as what? T sub what? A. T sub A stands for what? Antenna temperature. Yes? Okay. Now, what is the input total? Input noise power. Still waiting. Is what? K T A B, yes, plus K B. Did you get it? Is this a real temperature or this is a myth temperature? And it is the, where is this coming from? This equation is
5 minutes left, Professor.
what?
5 minutes left.
Yeah.
For sure.
From this equation. Clear? Good. Now, so the question, by the way, will give you S0 over N0. Are you following me or not? Okay. So S0 over N0 is what? Given. In the minimum. S0 over N0 minimum is given in question. Yes or no? Cannot hear you. Now, S0 is equal to what? G Sn. This is given. Yes or no? What is N0? It's G times what? K Ta. B plus what? Yes or no? What is this T equivalent? That's equal to what? F minus 1 times what? T0. Yes or no? And can you tell me what is the SI minimum? Which is the what? This is the MDS. Remember, one more time. This is given in the problem. Yes? I need to subtract from it what? This is in dB. Everything is in dB. Yes? I need to subtract from it the what? The noise power at the output. So what do I have? Equal to S over N0, the minimum, minus, by the way, what is this? This is in what? dBm. Yes or no? Help me. This is in dB. With the G. Agree? Okay. If TA happens to be T0, does it have to be? If it happens to be T0, what is this? Remember, T equivalent is what? F minus 1 times what? T0. Which means what? If this is T0, this term, the second term will what? Will cancel. And what do I end up with? SI, the minimum detectable signal, is equal to what? S0 over N0 min, help me, minus 10 log what? G K F T0. What? B. Did I mess up? 1 second. TA is what? What is the TA? Sorry, TA is T0. So what do I have? K T0B plus K F minus 1 T0B. You agree? Yes. So the KT0B cancels. So what do I end up with? K F T0B times G. Is this what you're on? G GB. Yeah. Clear? Clear? That's the minimum detectable signal. Now, in the real world, if you don't know, by the way, this, as we will see, this one is going to bridge for us the link budget to the what? Bit error rate calculation. Question. Does the link budget give you the bit error rate? By the way, do we know what the link budget is? we'll discuss it next time. But what I'm saying is that from the link budget, are you going to calculate the bit error rate? You are not going to get the bit error rate. You are going to get the bit error rate from either what? An equation, a cookbook equation, or you actually do what? Simulation. Did you understand what I just said? No. But this one is the one that will bridge the two analyses together. Why? Because it has the signal to noise ratio in here. And the bit error rate depends on the signal to noise ratio. Did you get my point or not? Yes or no? Okay. Now, if the question does not give you the signal to noise ratio at the output, the minimum, in the industry, usually, they take the minimum detectable signal to be roughly 3 dB above the noise floor. Above the noise floor. And remember, when you calculate the noise floor, you need to take into account the noise introduced by what? By the receiver chain. Did you understand what I just said or not? Yes or no? You assume that the minimum detectable signal is just a little bit, 3 dB, a little bit more than the what? The noise floor. But if the question gives you the signal to noise ratio, minimum signal to noise ratio at the input of the demodulator, you need to use this equation. By the way, none of these are in dB. Are you following or not? So if you want, if they are given in dB, it becomes what? S0 over N0 minus what? G minus what? K minus F minus T0 minus B. Are you following or not? If it is what? If it is all in dB. But if it's not in dB, you write it this way. Did you get it? No response. Did I still have time or ran out of time?
I think we just ran out. I'm sorry.
Okay, guys, by the way, all of you, happy Valentine's Day tomorrow. I don't know what that means, by the way. I don't know what that means, but I'm just being polite. That's all. Now, I suggest, by the way, that you get your what? You spend 5 minutes, get the gift, first of all. Make sure you get the gift. And then what? Excuse yourself to do the homework that I will be assigning. Are you following me or not? So, but make sure to what? Execute yourself after you get the gift, not before. It's too late before.
And this concludes EE 544 on Thursday, February 13th, 2014.